Most of what we know about atoms and molecules comes from spectroscopic measurements, where we shine light on a collection of molecules and we see which wavelengths of light are absorbed or emitted by those molecules. Let's try to understand that a little bit better on a more fundamental quantum mechanical level. So let's suppose that the state of our molecule could be written as psi, where it's going to depend upon the coordinates both of the electrons and of the nuclei. And using the Born-Oppenheimer approximation, we could write this as a product of two wave functions, one which depends only on the electrons but parametrically depends upon the positions of the nuclei, and another part that is basically a nuclear wave function, which is implicitly a function of the positions of those nuclei. So the little r represents the positions of the electrons, and the big R represents the positions of the nuclei. All right, now how does a spectroscopic transition take place? Well, light is basically an electromagnetic wave that oscillates in time, and it will preferentially interact with charged particles that are also moving in time. So basically molecules are made up of a bunch of charged particles, so that's the basis for which spectroscopic transitions occur. So one way we can quantify that a little bit is by defining an operator which we'll call a transition dipole, and that operator is given the symbol mu, and it basically consists of the positions of all the electrons, which I'll write like this. So the E is the charge on the electron, and the positions are given by this little r sub I. And also the charges that are distributed among the nuclei. So I'll add make a sum over all the nuclei times the nuclear charge, which we can write this way as the electron charge times the number of protons in the nucleus. And then that is also then related to the positions of those nuclei. So this is basically, this mu operator is giving us an idea of how the charges are distributed in a molecule. Both electrons, which are given here, and nuclei, which are included here. So the way that this works is that the probability that a transition can occur, say from state psi 1 to state psi 2, will be related to the means by which this transition dipole operator can connect these two states. So in other words, what we're really interested in is something that looks like this inner product integral over these two states connected by the transition dipole. So this is what's at the heart of it, and the probability for that transition is essentially going to be the square of magnitude of that. Now you may be wondering, this is a vector operator as we've written it here, and I've kept it as a vector in here. In fact, what really goes in here is a dot product between this vector and the electric field. And unfortunately, a lot of times we call the electric field capital E also, so it gets a little confused with energy. But if you'll just mentally program this in for this transition dipole, that gives us the interaction between the molecule, the charges on the molecule, and the field which interacts with those charges. All right, so when we perform this integral, it actually can be separated into two pieces. So if I take my capital 2 mu capital psi 1 and write this as using the Born-Oppenheimer approximation, it turns out that I can write this in effect as an integral that would connect the electronic parts of these two wave functions, which I'm denoting here, and it will also include a part that connects their nuclear wave functions. So this is nuclear wave function for 2 and a nuclear wave function for 1. Now I could write these out as integrals, but I hope you understand this notation. This is an integral around this operator, so it's like an expectation value of the mu operator dotted into the electric field of the radiation. And this is simply the overlap integral, if you will, between the nuclear wave function of the final state and the initial state. Now this particular thing here is something called a Frank-Condon factor. And there are different Frank-Condon factors depending upon the particular states that are included in here for the nuclear initial and final state. So these Frank Condon factors say something about the relative probability of making a transition from one vibrational level in state 1 to a different vibrational level in state 2, for example. But in all cases, we're talking about an electronic transition, so we're changing the electronic wave function, if you will, or the electronic state of the molecule when we shine light on it. All right, so what does this have to do with the price of tea in China? Not much. But what it does have to do with is whether or not a transition will occur. So for example, this particular integral sometimes can equal 0. And when it equals 0, that means that there is no transition. When it does not equal 0, then it means a transition can occur. And you might imagine that doing this integral is like orthogonal functions. If this happens to work out so that these functions are orthogonal when the the transition dipole operator is included in there, this would cause this not to occur. So as a result, this particular thing gives rise to something that we call selection rules. And these selection rules basically indicate conditions under which an electronic transition can occur. So what we're interested in are what are the particular conditions that allow this to happen? Well, there's several, and it turns out that they're related to all of the things that we have embedded in our term symbol for molecules. So I'll remind you that the term symbol for molecules looks something like this. And it could have, if it's a homonuclear diatomic molecule, it could have a G or U designation here. If it's an appropriate state, it could have a plus or minus designation there. But let's look in particular at these three things and what they indicate about selection rules, and we'll also say something about this. All right, first of all, in an electronic transition, spin cannot change. So in other words, this 2s plus 1 has to be the same. The multiplicity must be the same in the two states under which an electronic transition is occurring. All right, so another way we might write that is to say delta S equals 0. Delta S is change in the total spin, and it must be equal to 0. Okay, what about angular momentum? Now I'm going to distinguish between molecules and atoms because it's also useful to see what these selection rules have to say about atoms. For atoms, what we have is the general selection rules that for the orbital angular momentum, delta L can equal 0 or plus or minus 1. So it can change by 1 unit or it can be 0. However, it needs to be clear that a 0 to 0 transition is not allowed. Okay, you could have a 1-to-1 transition but not a 0 to 0. All right, similarly, for total angular momentum, delta J can equal 0 or plus or minus 1. All right, so again, 0 to 0 is not allowed when it comes to delta J. Okay, so this covers the selection rules for atoms. What about for molecules? Well, we no longer have L and J. What we have instead are the azimuthal angular momentum, which is this lambda, and delta lambda in this case also can be 0 or plus or minus 1. All right, so this gives us an idea of when we can expect to see a transition between two electronic states if we know their term symbols. Finally, let me indicate, and I'll put that separately over here, in the case of electronic transitions for homonuclear diatomics, the parity must change. So in other words, if I start with G, then I have to go to a U. If I start with U, I have to go to a G. But I cannot do either of these transitions. So these are not allowed. Okay, so we must change parity. So these selection rules are fairly simple, and not asking you to memorize them. You'll always have access to them if you need them for a problem. But to understand something about what they're implying about what is possible to do electronically and experimentally with a spectroscopy experiment and what is not possible to do.